So just to review what we talked about last day, we said friction depended on mu, how sticky objects were. Mu, Jake, had no units. That's why you'll see me in the notes, in the diagrams, I say mu equals 0.12. I didn't put units next to it. Friction is a force. That has units, newtons. We said the force of friction depends on how sticky objects are and not exactly how heavy the object is, how hard the ground has to push back up, which usually in Physics 11 was how heavy the object is. But I'm convincing you now, oh no, we're going to add extra forces in there. We're going to lift up. We're going to push down. We're going to change that. We're going to muck around with the normal force. So we finished looking at this example where we had 20 newtons, mu equals 0.12, 20 newtons. Oh, but this time we were also pushing down. And we said, oh yeah, if someone pushes down, it won't accelerate as fast because friction got bigger. Did the mass get bigger? No. Did G get bigger? No. Did mg get bigger? No. What got bigger? The normal force. The normal force. There can be friction on an object even when it's at rest. In fact, technically, there is two types of friction. There's what we call static friction and kinetic friction. We're going to pretend this year, Tyler, that there's only one type. This is my hashtag nerd trivia telling you the correct way and then saying, but I'm not going to test it that way. You may have noticed, have you ever tried to move something really, really heavy and slide something like furniture? Yeah. Is it tougher to get it moving or is it tougher to keep it moving? Okay, did you hear him? He said it's tougher to get it moving. That's the two types of friction. Static friction is always, the coefficient of static friction is bigger because the object has kind of really sunk into those microscopic hills and valleys. Once you get it moving, then there's a new coefficient of friction called kinetic friction. We're going to pretend those are the same thing. It's like if you've ever driven on a gravel road, if you go really slowly, you feel every single pothole. But if you go fairly quick, you skip over the puddles because your tires don't have time to drop all the way into the puddles. Okay. Anyways, so there can be friction on an object even when it's at rest because the hills and valleys lock up. The force of friction on an object at rest is called static friction. I'm just going to call it friction, Lewis. This is my being correct. So, suppose I pull on a desk with a force of 2 newtons. And the desk does not move. Which of the following is true? Static friction is greater than 2 newtons, static friction is 2 newtons, static friction is less than 2 newtons, or there is no static friction? What do you think?
B.
B?
Because the static friction is greater than 2 newtons.
Ah! We're going back. When in doubt, go to Newton's 3 laws. So he's going to Newton's first law. Newton's first law says if you have unbalanced forces, if friction was greater, you must accelerate. That's a law of the universe. So, is it accelerating? Are the forces unbalanced? No. Oh, and that also, not only does that get rid of A, that also gets rid of C. Oh, it also gets rid of D because if this was no static friction, that'd be ice. Oh, yeah, it's easy to slide stuff on ice. I'd hardly have to pull it all. So, A. My explanation, hey.
B.
Oh, B. Geez, Dewick. So into the teaching, I do the teaching wrong. B. Newtons first. If you got unbalanced forces, you're accelerating. If not, you're not. Objects at rest tend to remain at rest. Objects in motion tend to remain. What a stupid way to phrase it. That's how all my textbooks said it. And I was like, oh. Okay? So static friction is a weird force because it varies from 0. There's no static friction on their table right now because there's no sideways force on it, to a maximum value. So let's suppose the maximum value of static friction here is 30 newtons. If I pull with 10 newtons, is it accelerating? So how big is friction? Exactly 10 newtons. If I pull with 11.9 newtons, is it accelerating? So how big is friction? Exactly 11.9 newtons. If I pull with 29 newtons, is it accelerating? No. But as soon as I go to 31, that's when it'll start to accelerate. In fact, you know what? Right at 30, when it's tied, it's almost like mathematically it's on ice. It's teetering right on the brink, just a tiny bit of extra force, and it will accelerate because they're exactly balanced right there. Friction is a weird force. It's as big as it needs to be. Static friction is as big as it needs to be. Once it hits the maximum value, then the object will accelerate. So, you calculate static friction, maximum static friction as follows. Friction equals mu static, max, times the normal force. Again, we're just going to pretend for the whole lesson that friction equals mu times the, we're going to simplify and say whether we're moving or whether we're not, the coefficient of friction is the coefficient of friction is the coefficient of friction. Okay? But I told you it right. If the object is sliding, Tyler noticed, hey, once you get it sliding, it's easier to keep it moving. Now there's actually a new mu. What's mu? I don't know. What's mu with you? A whole new coefficient of friction. It's called mu kinetic because we're moving. And but it's still, can you see, mu times the normal force. So, for what it's worth, a 5 kilogram object sits on a surface with mu static is 0.3 and mu kinetic is 0.25. Determine the force required to move the object. To get it moving, well, here's our free body diagram. What are the forces acting on it? Get the obvious one. Is this object sinking into the ground? Is it flying into the air? Are there any other vertical forces, outside forces that this question mentions? Then I think I can say the normal force is the same size as gravity. Right? What else? We're moving an object. We'll call this F applied. You may notice if I'm drawing a picture, I assume we're moving it to the right. That's not a rule. That's just so all of our pictures look the same. If I am pulling it to the right, which way would friction be acting? To the left. Okay? Now, A says determine the force required just to start the object moving. Okay. That's going to be, just to get it moving, can you tell me which two forces have to be tied? Or can you tell me how big the applied force has to be to get it to accelerate at all, to get it to move at all? Looking at my free body diagram. More like just in my diagram here. How big does maybe I'm overcomplicating it. Doesn't the applied force have to be that big to get it? Okay, so I'm going to say as an equation, just to get it to move, it's going to be, but we're at rest. So really it's going to be this. The applied force is going to be mu static times the normal force. The 0.3. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. What? Got to be fussy, not 9.8. Read me the whole thing, Jake. The whole thing. Look, read me this whole thing. Read me those two letters, the whole thing. Just the two letters. Read me the two letters. And G. Not just G. Don't you dare just say G, because that's an acceleration, not a mg. That's a force, a mass times an acceleration. So I'm going to say it's going to be mu static mg. It's going to be, what is the static coefficient of friction here? 0.3. What's the mass? 5. What's G? Do I put a negative in? No, I took care of that with, I just want the magnitude. I'm just taking care of that with my winner minus loser approach. 14.7, but I wanted to walk through the reasoning. 14.7 what? It's a force, newtons. Once we get it going, well, first of all, B says the object is pulled with 10 newtons. Find the acceleration and the force of friction. Why can I say this without doing any math? Yeah. Was that a hint? Was that a... Well, friction. Now, I got to be fussy. That's the biggest friction can be. But that's how hard I have to pull to get it to move. Am I pulling that hard? No. But How big is the force of friction in this situation? Is it 14.7? Say no. How big is it? Gotta be, because it's not accelerating. No calculations there. Newton's laws there. That's all Newton's first. What if we pull it with 20 newtons? Will it accelerate? Okay, once it starts to move, the other coefficient of friction, the kinetic, the mu k, is the one I'm going to use. First of all, if it's accelerating, who's winning? Okay, who's losing? So here's my equation. Where the force of friction now, well, that's going to be mu times the normal force. Which mu? The moving one. The 0.25. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. G. So it's going to be 0.25 times 5 times 9.8. The force of friction is that. Yeah, it would be easier to push. 2 newtons easier, roughly. Actually, 2.5 newtons easier to push. 12. I'll call it 12.3 newtons. Then to find the acceleration, hey Quinn, how would I get the A by itself? No kidding. Really? I like that. So if I hear you correctly, and I think I do, you're saying it's going to be the applied minus friction divided by m. What's the applied force in C? Read in C. What's the applied force? In part C, it tells you. 20, right? Minus, what's friction? Now you said 12.3. Did I round that answer off, Quinn? Say yes. So I would be clever and I would actually use the 12.25 in my calculation. Yes? In fact, I'm going to use my answer button. And what's the mass? Please tell me they told me. 5? You know what? I think I can do this in my head. 20 take away 12 is 8. Take away 0.2 is 7.8. Take away 0.5 is 7.75. Divided by 5. Dividing by 5 is the same as time. Oh, good gosh. 7.75 divided by 2 is going to be 3.5. No, 3.875. It's in the morning. My brain isn't quite okay. In brackets, because there's more than one number on the top. Divided by 5. Wow! I was totally off. 1.55. Wow. Do it. 1.55 what? Units. It's an acceleration. Meters per second squared. Okay. Got a couple of videos. I'm going to give you lots of practice, but I also little thought experiment. I think I forgot to add the homework to the video, so I've now added 7, 8, 9. 8's tricky. 10. Skip number 11. 12, 13, 14, 15.